So the Association of Ammonia Refrigeration was formed in 2012. The purpose of this association is to promote safe and efficient use of ammonia refrigeration and to provide technical guidance, seminars, and of course newsletters, other publications, and online information. AR has been keen and has been disseminating knowledge continuously throughout its foundation. This is our current board of members. You can see that the people are from manufacturing industry, contracting industry, the engineering segment, product manufacturing. Different segment of the people are there as part of this board members which are technically expert. We have been doing a lot of training programs and continuously sharing information with you through various programs, through very venues like Advantage Ammonia training programs, technical presentations to other platforms, webinars, and of course the Archon. We will talk more about Archon soon, and also the networking events, newsletters, other publications we have. And we have members from various countries. These are our current corporate members, and we specifically thankful to them for supporting AR, and whatever we have achieved is because of the support of these corporate members. I encourage all to become corporate member, so as to promote safe and efficient use of ammonia refrigeration and bring in the knowledge to all the members. These are our publications. These are available online from AR website. You can order it through AR website, or you can send the email to ammoniaindia@gmail.com. This books covers Ammonia Forever, which is a in-depth knowledge of ammonia as a refrigerant. Our newsletters, AR standard for closed loop ammonia system design, our operation maintenance book, cold storage design book. We have our plant operation safety flyers, and of course a pocket guidebook for ammonia refrigeration. The standard has been now converted into Indian standard, and it's available from BIS as standard. We have been conducting various programs, training programs in person and also on online and various platforms. We have this year we have conducted first training program in April, which was conducted by Paran Spesar and Mr. Gulanikar sir. Then we had ammonia webinars online in June and July. So those are the very as an AR, we do not support or promote any company or product. We share knowledge. So these technical presentations, seminars are also completely technical based. And you can see some glimpses of these programs here. Then we had an online program considering the World Refrigerant Day on different speakers from different part of the world. And we are thankful to our sponsors who help us to make this online program possible. Our Advantage Ammonia program, we again arranged in the basin or in the cold storage basin of Sangli, where you find a lot of cold storage for resins and potatoes. And there we conducted a program where people talked about different operations, how to operate the plant, what are the safety precautions, how to improve energy efficiency, what is the actual performance difference between ammonia and synthetic refrigerants. Various topics were attended by various experts from different parts of the industry. Online webinars we conducted about how to optimize cold storage design, driving process safety excellence through ammonia refrigerant systems, new HFO refrigerants and their impacts on environment. This was a very important seminar because many people, when they talk about new refrigerants, they don't talk about their impacts or how harmful they are to our earth and human being. So that was very well explained by Mr. Alex Zanderkor Pachai. Then we have harmful effects of water, dirt, and oil in ammonia refrigeration systems, which was talking about the what worst things happen in the plant. Then there was a sustainability with ammonia as a refrigerant, how your plant becomes sustainable in different applications, and how ammonia makes your plant last long, more energy efficient. All these topics were discussed throughout these online webinars. We do participate in different exhibitions. This year also, our team will be there in China refrigeration next month in April, and we'll be happy to meet you. If any one of you are coming there, please do reach out to us, and we will definitely like to meet and interact with you. Then we participate in many other exhibitions also, where our members, our president talk about ammonia refrigeration, and discuss about the technologies we do. Arcon, Asia's only convention on ammonia refrigeration, and which an exhibition this year happened in Hyderabad. It was the first time we did it in Hyderabad Gold Hotel, and we are specifically thankful to our event partners Evapco, Freak, Manik, Kirloskar, Hermetic, FinTube, MFinTube, Zilabek, Indotech, Omega ISIL, USM, and Flowdyne. Also, our participants were there for the exhibition also, and this was very well received by the people from Hyderabad, Telangana, and nearby states. Also, a lot of people travel from Pune and Mumbai, which was a main boost for us. And we really appreciate efforts taken by our committee members to make this event successful. We had different speakers coming from the different part of the world. We have Kurt Leibendorfer. Please pardon me if my spelling, I'm a little bit not able to pronounce it correctly. He came from USA. Mr. Igashira, a well-known figure from Japan. Mr. Kushal came from USA Kargil. Then we have Ron Hoffman and Rob Vader from GIA Netherlands and GIA Germany. So everybody was expert in their field and did talk about their expertise. They share their knowledge and new things happening into the exhibition. It was a full packed day for all delegates, and I appreciate the people enjoyed the technical know-how sharing into this, which was followed by a wonderful evening dinner. These are some of the glimpses of presentations and speakers who joined us into this show and had a great evening. So now we are planning to do Arcon next year in January, most probably around 28th to 30th January in Ahmedabad, and date and venue will be announced very soon. So we all look forward for your participation in the event as a delegate, as a sponsors and stallholders. Join this event so as to make it a great event, and share your expertises with this. And what we have our website ammonia.org. For members, all the presentations of various programs happen in AAR are available for free download. Today's presentation will also be available for free download for 1 week from tomorrow onwards. And we have a membership, online membership application, information about ammonia. There is some FAQs about ammonia and other information on website. So I encourage you to visit our website www.ammoniaindia.org. Also, do not forget to like and subscribe our pages on LinkedIn and Facebook, so that we all can get connected and share more and more information about it. The memberships, as we have, as I told you, we have corporate membership and the individual membership. So I encourage most of the companies to join as a corporate and attain various benefits which are available
Introduction.
as a membership. And then we request all of you to mute your mics so that you can hear presentation very well and listen to Paranspe sir. we want to conduct training programs in various cities across India, and if get the opportunity outside of India also. So we request members to come forward and join us into this conducting program. Share your information, your knowledge, or your interest to conduct these programs, and we'll be happy to be with you. We are working on. We have actually completed now compressor standard and given it to BIS. So waiting for them to come out, and we'll be making more now. Some publications also very soon it will be launched, and other options are there. They're trying to go for a more user-friendly website, and maybe we'll come out with the mobile app also. Let's wait and see what we can do. But we expect all of you to contribute in a way it is possible for you. Please remember, this is a voluntary organization. Everybody contributes here voluntarily. Even speakers, presenters, they contribute voluntarily. AR do not pay anyone for their contributions in AR. So this is a voluntary work for everyone. Request all of you to join AR. Send your interest, your ways you can contribute to AR. You can reach out to AR secretary or AR office in using AR mobile number and AR and AR. I request all of you to switch off your. Hello. Hello, am I audible now? And can you hear the Paranspecer's presentation? Can you see the Paranspecer's presentation? Yes, thank you. So now I request Paranspecer to start with his presentation.
Okay. Good afternoon to everyone. Good morning, good afternoon, whatever is the time in your region. Today's presentation, as Anand has explained, we are going to talk on design of heat exchangers for ammonia refrigeration process cooling plants. Now, this is particularly a presentation along with some of my experiences, which I felt we should share with all of you and my execution of projects. My first slide shows what are the heat exchangers we use in ammonia refrigeration plants. The main heat exchangers which we use are shell and tube condensers, evaporative condensers. Then so many plants use heat recovery exchanger in the discharge line to generate warm water. Then shell and tube evaporators for water chilling as well as brine chilling, plate heat exchangers, condensers and chillers, then falling film water chillers, and many other types of heat exchangers. But we are going to concentrate today more on shell and tube condensers and chillers. Now I'm going to make this presentation is FPS unit and not in SI system, which is currently being followed by most of the people. But I'm giving the explanation why we follow what we are going to follow in FPS system. The first point is in FPS units, all calculations are on per hour basis. Whereas in SI systems, as you know, watt is joule per second. So every time we do any calculation in watt or kilowatt, we have to either multiply to 3600 to get per hour kilowatt per hour, or divide by 3600 if kilowatts are given to do the calculations in joules per second. The number two is temperature scale in FPS system is much wider. It is from 32 degree Fahrenheit to 212 degree Fahrenheit for water boiling point and freezing point. As against in centigrade, it is 0 degrees centigrade and 100 degrees centigrade. So as you can see, the calculations are more accurate in a FPS system. And the third point is the atmospheric pressure also in FPS system is 14.7 psig. Actually 14.696, but we round it off to 14.7 psig. Whereas in SI system, it is 1.033 kg per centimeter square. So it is very compressed. Specific heat of water in FPS system is 1 BTU, whereas in SI system it is 4.186 joules per kg degree Kelvin. So calculations become a little complicated. It is also easier to remember whole number than the fraction. For example, we can remember 10 psig instead of remembering 0.703 kg per centimeter square. So I hope you agree with my observations, and I will continue further. We have initially indicated all these standards which are used in design of pressure vessels. I'm not going to read all the standards, but the most important standard is ASME Section 8 Division 1, which is rules for construction of pressure vessels. This presentation will be available on our website, so you can see all these standards. The next important standard is TEMA standard, Tubular Exchanger Manufacturer Standards Association, and of course our IS standard 2825, closed circuit ammonia refrigeration system, code practice for unfired pressure vessels. So these are the three major standards. Now, when we start designing pressure vessels, the first question comes up: at what pressure do we design it? So the standard as per our air standard, 21 kg per centimeter square for water cooled applications, 27 kg for air cooled applications. These are our AR standards. But if you go to EN standard or ISO standard, they also suggest that you can design the pressure vessels 17 degrees above wet bulb temperature if it is water cooled application, or 17 degrees above dry bulb temperature if it is air cooled application. Of course, for ammonia plants, the air cooled applications are comparatively less than 5%. Most of the applications are water cooled applications. I always prefer in my projects designing both high side and low side pressure vessels for the same pressure, so that anytime you close the plant, you don't have to pump down the liquid from the low pressure side into high side ammonia, and thereby you reduce the quantity of ammonia receiver size and as well as you don't have to every time rush to pump down the system. The now design precautions. We shall start with construction of the pressure vessels first and then selection of the pressure vessels. The first question is, we use boiler quality plates IS 2825 or SA 517 grade 6070 plates. Now the question arises, first question, why do we use these? Why not use 2062, which is a structural steel? The structural steel is not used because it is carbon content is not controlled. We
कुछ साउंड का इशू है, म्यूट हो गया। म्यूट हो गया, म्यूट म्यूट हुआ।
Yeah.
Okay.
Are we audible now?
Hello. Okay. So this is why whenever we refer to any standard and they indicate that use this, we must ask ourselves why they have indicated. Going into deeper into the question always gives us better understanding of the subject. Then next is use proper thickness of plate as per TEMA standards. Considering joint efficiency as 0.7, if you are not going to do any radiography while construction, but if you do radiography, then it can be 0.85 or 1%, 100 depending upon whether it is 10% radiography or full radiography. Then after you do the calculations, add 1.6 mm as a corrosion allowance for whatever thickness you have calculated. The fabrication should be as per ASME Section 8, Division 1 or ISO 16521, 528. How to calculate now the pressure vessel calculation. Lot of places I have found that people use unnecessarily very thick plates without going into the details of calculation. That is a wastage, our national wastage of raw material. So we must use exact optimum thickness for any calculations. The material of construction we are considering SA 516 grade 70. Now, if you see the property of this material, the allowable stress is 17,500 pounds per square inch as per ASME code. Let us design a vessel of 30-inch diameter, 12 feet long. Now, how to calculate the thickness? The calculation for thickness formula is pressure into internal radius upon allowable stress of the material into joint efficiency minus 0.6 times the internal pressure. Now, as I mentioned, the joint efficiency 0.7 if it is only DP test, dye penetration test. But if you do 10% radiography, it is 0.85. And if you do 100% occupancy, joint efficiency is 1. What does it mean? That if you do radiography, your thickness of the pressure vessel will come down and you will be able to save on the material. Then allow afterwards a corrosion allowance of 1.6 mm. I have just given this calculation of pressure 300 psi, which is 21 kg per centimeter square, internal radius 15 inch, uh, this allowable stress is 17,500 psi, and let us assume joint efficiency 0.7. We are not carrying out any radiography. So the thickness will be 300 psi into 15 internal radius divided by 17,500, that is allowable stress, into 0.7 minus 0.6 into the pressure, as per the formula given on the earlier page. So the thickness of the calculation is 0.37 or 9.4 centimeters. Add corrosion allowance 1.67. So the thickness requires becomes 11.07 millimeter. Now these plates are not available, they are available in standard sizes. So next available size is 12 mm. So use 12 mm thickness plate. This is how to calculate appropriate thickness of the calculations. I have seen in many places people use unnecessarily 14 mm, 16 mm, 18 mm thickness plates. That is a wastage. I have just given for the sake of ready reckoner what thickness should be used if you use 24-inch dia, 30-inch dia, 36-inch dia, up to 40-inch dia. Maximum thickness is 18 millimeter up to 48-inch dia. Normally, we don't use any pressure vessels higher than 48-inch dia. Normally, 24-inch or 16-inch, 13-inch, 36-inch. The dish end thickness is also given. This dish end thickness is spun dish end. Don't use the fabricated dish end. The fabricated dish end, what happens if you fabricate the dish end out of a plate? When you are making a dish end, the thickness at the radius goes down and the dish end becomes weak. So that is the point where the chances of breakdown can take place. So always use the spun dish end, which is readily available in the market, where the thickness is uniform all across the dish end. So this is very important point if you are using dish end. Now, welding practices. The welding practices are also important, not only the raw material, but you have to use root run, that is TIG, what we call tungsten inert gas or argon gas, or MIG, metal inert gas for vessels. Now, again, if you ask me, why do we use these? Why not use ordinary electrode 601, which has structural welding rods? The reason is when the welding is taking or MIG inert gas, it is a clean, defect-free weld material. Protection or the penetration is very deep up to the end. The protection from oxidation takes place. So there is no slag formation. Normally, if you use structural steel, there will be a slag which will go inside vessel, which cannot move. The vessel is welded, and that slag will ultimately be carried to the compressor, and your compressor will have problem. So therefore, use these TIG or MIG welding electrodes for the basic root run, the first run. Electrical welding rods also are important. E7018. Do not use 6013 welding electrodes. Then one of the most important points, if you are doing the welding anywhere on an installed plant, remove all valve internals, because valve internals could be of rubber, neoprene, or some other material which cannot withstand such high temperatures which come during welding. Remove all controls, remove all strainers, remove all solenoid while before doing any welding. If you don't do this, your controls will or some parts may get damaged. The two vessels we are going to consider are conventionally designed from evaporator design. And these are both shell and tube vessels, which we are going to discuss. This is vacuum pressure and enthalpy diagram, which shows the operation of evaporator, condenser, and the expansion device. As you see, evaporator, the inlet action, but in ammonia
सरप्राइज की वो क्या प्रेजेंटेशन देने वाला है
normally use accumulator, and we separate out that gas formed into the during expansion and allow 100% liquid to come into the flooded chillers. Therefore, ammonia plants are always more efficient as compared to direct expansion HCFC plants. So this is important point to remember. What is the difference between a DX plant and a flooded plant? 99% ammonia plants are either flooded plants or pump circulation systems in which 100% liquid enters the evaporator. Let us talk about now condenser design. A shell and tube condenser design, when the end covers are removed, the tubes are in triangular pitch and distributed throughout the periphery or right up to the top. What is the advantage of shell and tube condenser? Now that there are many types of condensers. Mostly we use evaporative condensers also, but there are certain advantages of shell and tube condensers. It is a compact construction and can be used in skid-mounted factory-assembled condensing unit. For example, a lot of people are now manufacturing ammonia units and putting them into containers, mobile containers. In that container, you can use shell and tube condensers, which is more convenient than other types of condensers. The condenser is installed generally in the plant room. So the piping is very small. Compressor to condenser piping becomes very small. If you use evaporative condenser, the piping could be pretty large. The water consumption is less compared to atmospheric condenser. I'm not comparing with evaporative condenser. Evaporative condenser also water consumption is low. But compared to general atmospheric condenser, which is an open condenser, the water consumption is compared to that is less. In containerized system or on the rooftop unit, I have seen many now ammonia units installed in USA on the rooftop. So a package unit completely of ammonia condenser, ammonia chiller, water cooled chiller is installed on the rooftop, and then even if ammonia leaks, it leaks into the atmosphere without affecting any occupancy areas. So these packages are becoming pretty popular now even in countries abroad, especially Europe, of course, uses a lot of ammonia, but Americans were a little bit against that. But now they have realized the importance of ammonia, and now they are using it also. Now let us see what are the equations we use for calculation of condensers and chillers. The two main equations is Q. Q is the heat transfer rate in BTU per hour equal to M, that is the mass flow rate pound per hour, into specific heat BTU per pound per degree Fahrenheit, and delta T is the temperature difference between inlet temperature and outlet temperature of water. For example, normally in India, our wet bulb temperatures are around 28 degrees centigrade. So water entry temperature is 32 degrees centigrade, outlet temperature is 36 degrees centigrade, and condensing normally we design at 40 degrees centigrade. With evaporative condensers, you can go as low as 38 degrees centigrade. This equation number 2 is also Q equal to UA into LMTD. What is U? U is overall heat transfer coefficient, BTU per hour per square feet per degree Fahrenheit. A is the area of heat transfer in square feet, and LMTD is the log mean temperature difference, that is delta T1 minus delta T2 upon log to the base of delta T1 upon delta T2. If you see in condenser, what happens? The condensing line is constant, whereas your water temperature is increasing from 32 to 36 degrees centigrade, condensing temperature remaining constant. So delta T1 is temperature minus water temperature, and delta T2 is condensing temperature minus outlet temperature. Since the condensing temperature is constant LMTD, as I told you, for 40 degrees condensing temperature and with water inlet temperature of 30 degrees centigrade, delta T1 will be 10 degrees centigrade and delta T2 will be 5 degrees centigrade. So LMTD will be 7.2 degrees centigrade. Having calculated this, let us look at this again, the pressure enthalpy diagram. If you see the top line, the condensing line, you will find after the compression, the gas is in superheated region. So the condenser has to function by removing three types of heats. One is the superheat, which has to be removed. Then the liquid, once it reaches the saturation, then it is 100% liquid. That liquid needs to be cooled to condensing temperature. And then if at all, if you are using, then some subcooling is involved. But in ammonia plant, generally, we rarely use this subcooling subcoolers, because the moment we use subcooler, it leads to increase in superheat, and increase in superheat, gamma compression index of ammonia is very high, and it leads to very high discharge temperatures. So as far as possible, we don't use suction liquid subcooler in ammonia plants. But remember, this is the line very important. I will tell you my experience. One of the plants which was designed, a very big petrochemical plant, the capacity was 100 ton. The gentleman who was designing the plant, a very well-known expert in this field, designed condenser also for 100 capacity. And what resulted? There were 9 units of 100-ton capacity. It was a very big plant. And as soon as we started the compressor will trip on high discharge pressure, because the condenser was designed wrongly. The condenser, it was minus 30 degrees centigrade plant. So the condenser heat rejection becomes nearly 1.6 times more than the evaporating tonnage. So the condenser size should have been of 160 tons. Instead of that, it was designed for 100 tons. And unfortunately, that plant never worked and it had to be closed down. So be very careful when you are designing condenser heat rejection, which should be equal to evaporating capacity plus work done by the compressor, as the lower line shows. Refrigeration effect plus work done by the compressor is the total heat rejection in the condenser. For example, a compressor working at 40 degrees plus 5 degrees has a capacity of 100.74, and the power consumption is 20.72. So the condenser should be designed for 121.46. That is the addition of both these two. So the ratio is 1.2. But if you go to a lower temperature, you see the power consumption for the same capacity as high as 67.32. So your ratio becomes 1.66. So the condenser should be designed 66 times bigger, that is for 168 kW capacity. Remember, this is very, very important point. Many of the plants I have seen people neglect this. Now, resistance, when we calculate UA delta T, what U means? U is a resistance, 1 upon the resistance to the heat transfer. Resistance to heat transfer consists of 4 components related to overall heat transfer coefficient. That is refrigerant sign film resistance, tube wall metal thickness resistance, fouling deposits resistance, and water film resistance, assuming at 10 feet per second velocity. So water film causes resistance, fouling deposits cause resistance, cause resistance, and of course refrigerant film. All one upon addition of all these resistance, reciprocal of that will give you the U value. The important subject is important is fouling. Many times people neglect this fouling of the tubes. Tube fouling, water side fouling disastrous, and it can be classified into following categories. Particulate fouling is the actual mud or other undissolved solids, precipitation, corrosion because of the hardness of water, and biofouling, algae and other materials, chemical induced corrosion. These are the 4 or 5 factors which contribute to fouling of the tubes. In HVAC applications, fouling of the condenser tubes substantially impacts the power consumption of the compressor. This is why the focal point of any water treatment program should be prevention of emission. I have seen one installation in Pune where they used plate heat exchanger for condenser, and the condenser was the plate heat exchanger manufacturer was of course chemical cleaning that every 3 months, every 6 months, the direction of flow was changed, every precaution was taken. In spite of that, the entire plant blew up. Why the plant blew up? Because the operator had bypassed discharge pressure cutout because it was constantly tripping on discharge pressure. Why it was tripping on discharge pressure? When we opened that PHE condenser, it was totally coated with mud. So you couldn't see even the corrosion, even the slots on the plates, and it was like a flat plate. It had to be entirely scrapped out mechanically to make that condenser work again. But the client became wiser and he changed the condenser to shell and tube condenser. The other alternative is if you are using PHE, use RO water. It is always essential to use a water treatment plant. A layer of scale of 1/64 inch in thickness on the condenser tube can increase the electrical usage in a chiller as much as 33%. So you can imagine why we must take care of removing this fouling and cleaning the tubes. That is very essential. Cleaning of the tubes is also important. Cleaning of the your cooling tower is important. People who don't drain the water, so the water hardness, what evaporates is a distilled water, and in the tank the hardness starts increasing. So you need to drain equal amount of water what gets evaporated. Nobody does that. That is the most neglected component. That is cooling tower, and with the result, all that hardness goes into your condenser tubes and creates big problems. The biofilms can decrease condenser heat exchange also. So this is the fouling condenser tubes and fouling of corrosion, mud, etc. Everything accumulated in the tubes. Refrigerant film fouling. What is the oil in the refrigerant causes resistance to heat transfer, and some oil which is carried in the system causes a very control oil in a system occurs when the heat exchange tube becomes coated with oil. So removal of oil using a very high efficiency oil separators. So minimum oil is carried in the system is very, very important. The ammonia and oil, they travel throughout the system, and everywhere we have to have oil drains at the oil separator, at the receiver, at the evaporator. So instead of that, if you use a demister pad SS oil separators, your oil carry forward will be reduced and your fouling will also reduce. The heat transfer efficiency is reduced drastically if it is fouled and reduces the cooling effect. Now we go to shell and tube condenser selection calculation. We discussed how to construct the shell and tube condenser. Now we go to selection. Let us decide that we are going to select a refrigeration condenser of 100-ton capacity. The cooling water inlet is 30 degrees centigrade, outlet is 35 degrees. As I mentioned, condensing 40 degrees centigrade. Temperature is degrees centigrade. Why we are assuming evaporative temperature for calculation of condensers? Because we need to calculate what is the work done by the compressor that needs to be added into this in the condenser. Step 1, calculate total heat rejection. Evaporator is 100 into 12,000 BTU per hour plus compressor BHP 124 power consumption into 45 into at 52 BTU. Step 2, calculate water quantity required. The total heat rejection is equal to 60 into 8.33. 60 is minutes. 8.33 is pounds per gallon into bracket water leaving temperature minus water entering temperature. Now this 8.33 into 60 is multiplied. So normal formula people use is 500 into GPM into delta T. So 1,52,057.60 equal to 500 into GPM, and water I have converted degrees centigrade into Fahrenheit. So GPM of water required is 339 GPM of water is required. So first step is to calculate water quantity. Step 3 is determine mean temperature. As we discussed, it is mean temperature. The delta T1 is 104 minus 86 is 18. Delta T2 is 104 minus 95 is 9. So LMTD log mean temperature is 12.92. Now we have to assume certain tubes per pass to start with. So assume 30 tubes per pass we use. So GPM per tube per pass will be 11.3 GPM. The next step is find the velocity of water by multiplying by 21.8. Now this 21.8 is a ratio for tubes which are used 1.25 diameter or 1.06 internal diameter. This ratio will vary as the diameter of the tube will go on changing. For 1.06 ID, it's 21.8. How this has been calculated is a detailed calculation. We are not going into detail of that, but if required, you can send me a mail. I will provide these calculations. Normally, why we are selecting a velocity of around 250 to 300 FPM so that the pressure drop and the pumping power comes down. So this is an indication for quick selection of LMTD. You can calculate it also or use T1, T2 and join a line. The center line will give you an LMTD calculation. Now we are calculating now heat transfer coefficient. Now we have seen water velocity 250 FPM. If you take a straight line from 250 FPM upwards and let us assume we have not treated the water, cooling tower water. So we intersect this line at a particular point on the below line, and then the go horizontally towards heat transfer coefficient. You will find the heat transfer coefficient is around 165 BTU per hour per square foot. So from the graph, heat transfer coefficient that was approximate, actual is 172 BTU per hour per square foot per degree Fahrenheit. So the area required becomes total heat rejection divided by U into LMTD. Area required is 688 square feet. Add 10% safety factor for fouling, etc. So 757 square feet. Select a condenser size, which is a standard size. You can't manufacture a size every time new one. The manufacturers have standard sizes: 20-inch diameter, 24-inch diameter, 30-inch diameter. So we select next size, 24-inch diameter, 15 feet long, 174 tubes with 855 square feet area and 6 pass arrangement. So around 29 tubes per pass from the standard available catalog. Now we need to calculate the number of passes and the pressure drop. The internal diameter is 1.06 diameter. The number of passes, the formula is indicated pi d square into FPM into 62.4 pounds per cubic feet divided by pi by 4. So 4 divided by 4, square inch is converted into square feet, so divided by 144. GPM is converted into pounds is 8.33. So this is number of passes. Number of passes, if you calculate, it comes to 6 pass. So pressure drop on the water side from the catalog, you will find it will be around 0.7 kg per centimeter square, which is moderate, and therefore we decide that our calculations are correct, our velocity is correct, our selection is correct, and our calculations are also correct. So now we go to next vessel, which is shell and tube flooded chiller. Now if you see the cross section of this shell and tube flooded chiller, you will find, unlike condenser, the tubes are not right up to the top. There is a large area left on the top of the tubes, because ammonia, when it vigorously boils, the lot of possibilities are there of liquid coming to the compressor. So in order to avoid liquid coming to the compressor, the tubes bundle is a gap is left because ammonia boiling heat transfer coefficient is very high, and possibility of droplets entering into suction line are there. We'll discuss subsequently what is the advantage of surge drum, but while manufacturing chiller also, a precaution is taken. The tubes are not filled right up to the top. I came across one design, a chemical manufacturer, a kettle type evaporator in a Gujarat plant, in a Baroda petrochemical plant. And they said, we are going to manufacture heat exchangers. You don't provide us the heat exchangers. And he used this kettle type heat exchanger as per their chemical engineering design. The chemical design or kettle type design has the tubes right up to the top, up to in the vessel. A little bit gap is left, as you can see in this vessel. With the result, what happened, whenever they started the plant, the liquid used to come to the compressor. And the entire plant was designed by me, and they called me to the site. But they say, we cannot show you the plant because it is our secret technology. I said, if it is secret and if you can't show me, then I can't analyze what you are doing. So when I visited the plant with great reluctance, they took me to the plant and showed me the plant. And the moment I saw the chiller, I saw that the liquid is coming because there was a frosting on the line which was taking place. There was no surge drum. Directly the outlets were connected. These three outlets were connected to the suction line going to the compressor. I said, this is incorrect design in refrigeration practice. You have to provide on top of a chiller a surge drum. So if you see this next slide, on the chiller, on the top of that, there is a big vessel, which is a surge drum. Now, surge drum is not so important diameter wise or length wise. You must look at these pipes joining the shell and tube chiller and the surge drum. There are 4 or 5 pipes have been installed. Why have they been installed? The question arises that why they have been installed, why not single pipe? I have seen one also installation where there was only one pipe, and the customer, when I was doing some presentation, he came and he says, when I load the compressor on 4 cylinders, the liquid does not come to the compressor. But when I fully load the compressor, 6-cylinder compressor, the liquid starts coming to the compressor. So people are asking me to change the chiller design and the surge drum design. I said, don't do anything. Just increase this pipe joining the surge drum to chiller from 1 pipe to 3 pipes, and your problem will be solved. So without spending any money, which is very minimum amount, his problem was solved. Remember, the liquid coming to the compressor is a general phenomena. Liquid comes to the compressor in 4 different forms. One is liquid slug. That is, when you defrost the system, suddenly the liquid shock comes and the liquid comes to the compressor. The second is continuous migration of liquid coming to the compressor, which was taking place in this particular case. The third is liquid droplets, small liquid droplets coming to the compressor. That how can you make out liquid droplets? Because your valve plates, your other piston rings, etc. will break if droplets are coming to the compressor. And the last liquid coming is in the form of mist. If the mist is coming to the compressor, it is also a liquid mist, and that will damage your valve plate. There will be itching on the valve plate. If you see the valve plate, there will be itching on the valve plate. So this is how the liquid comes to the compressor, not only by way of liquid format. It can come in these various forms, and we need to avoid all these forms. Therefore, this velocity to be maintained in the surge drum is very, very important. The velocity to be maintained in this surge drum should not be more than 50 to 75 feet per minute. So design these pipelines for this velocity, and you will never have a problem on your compressor breakdown. The next point, we design brine and their applications. Let us look at what are the brines. Brines are secondary coolants used in refrigeration system for 0 degrees below temperature. Water cannot be used below 0 degree because it will form ice. So the brines are used for low temperature applications. What are the common brines which are normally used? For a commercial plant, lot of people use sodium chloride brine. For example, in block ice plants, they use ordinary salt as a brine, which has a temperature up to minus 15 degrees centigrade. Dairies, block ice plants, they use sodium chloride. For a little more advanced systems, a calcium chloride with up to minus 45 with some agents added into it needs to be used. So calcium chloride is used up to minus 45 degrees centigrade and is very popular in cold storages, freezers, etc. Normally, the process plants, industrial process plants, they use either ethylene glycol or propylene glycol. Both these can be used up to minus 50 degrees centigrade from minus 10 to minus 15. Now the question arises, what is the difference between ethylene glycol and propylene glycol? The propylene glycol is food safe. It is non-toxic. So wherever there are food plants, propylene glycol is preferred. Whereas it process plants, industrial chillers or ethylene glycols is preferred. Ethylene glycol has lower viscosity and your pumping power and other thing will be slightly lower. Next slides will show you heat transfer coefficient comparisons of various refrigerants. Propylene glycol has only one, whereas R11 ethylene glycol is nearly 40% more heat transfer coefficient. Therefore, ethylene glycol is more popular. Methanol water, sodium chloride, calcium chloride, all of them are having much higher heat transfer coefficients. This propylene glycol is one. Now I will tell you another interesting example of use of propylene glycol. In one of the Bombay plants, they were using propylene glycol for chillers, shell and tube chillers, and it was German design plant. At the evening at 8 o'clock, I got a call that your plant design is totally wrong and constantly the liquid is coming to the compressor. So come down immediately. All of us are waiting even at night time. So I rushed to Bombay. In those days, it used to take 4 or 5 hours, minimum 5 hours to reach Thana. When I reached the plant, I saw that really the liquid is coming to the compressor. I was confident about my design of chiller, surge drum, the location of float switches at various places, that is 50% liquid level, 65-70% compressor trip, 15% ammonia pump trip, etc. Everything was okay. Still, I was wondering why the liquid is coming to the compressor. Then I said, I want to see your design calculations. Please bring your file. When they brought the file, I saw they had purchased propylene glycol from one of the Bombay suppliers, and they had specified in the purchase order propylene glycol 30% concentration. And what they had done, as the propylene glycol came in drums, they charged the entire propylene glycol into the system without making a 30% concentration. So 100% propylene glycol was charged into the system. Now, as you can see from the earlier side, the heat transfer coefficient is very low. No heat transfer was taking place, no evaporation was taking place, and entire liquid water was filled up into the chiller was coming to the compressor. Finally, what I have to do, I have to drain entire propylene glycol, replace it with water. Continuously, I was pouring water into the chiller, draining out the concentrated propylene glycol. When the concentration came nearer to 40%, 30%, then the liquid coming to the compressor stopped and the plant started working. But the German people accused me so much that they said this, we were telling client that don't buy the plant from India, buy the plant from Germany. Our plant is always better. So we should have a confidence. We should have a fundamental knowledge. A fundamental knowledge is very, very important if we are designing anything. We must always ask why we are doing this. What is the reason behind it? What we must do to avoid problems? Then there will be no problem. I have designed nearly, as Anand Saab has said, nearly 700 plants, but nowhere I have faced any problem so far. So this third drum on the chiller, these pipes, which are very important, arrow shows more than one connection to reduce the pull velocity. Now let us design one ammonia flooded chiller. Basis of design 100 TR. Here we don't have to take compressor power consumption into account. We can design the chiller for exact capacity, whatever the customer requires. Brine inlet temperature 0 degrees centigrade, brine outlet temperature -5 degrees centigrade. So average brine temperature is 2.5 degrees centigrade. The brine concentration is 30%. Viscosity or mu is 2.5 cp. Brine freezing point should be always at least minimum 10 degrees lower than the brine outlet temperature. Here the brine outlet temperature is -5, so brine freezing point should be at least 10 degrees below that. So such concentration should be selected. Brine specific heat 3.8 kilojoules per kg. Brine density 1030 kg per meter cube. You will be wondering why I'm taking these calculations in SI system. I want to show you also in FPS system, but some people will say, oh, we follow only SI system. So for their benefit, I am showing calculations also in SI system as well as in FPS system. In SI system, calculate brine flow rate using the same formula mCp into delta T. So kilojoules per second, 3.87 kilojoules per second, kgk into 5 degrees delta T. So mass flow rate is 1030 is the density. So mass flow rate is 0.018 meter cube per second or 65 meter cube per hour. Ammonia evaporating temperature -10 degrees centigrade. Latent heat of ammonia at -10 degrees centigrade, if you see from the chart, it is 1050 kilojoules per kg. You will always find this joule, J has to be written in capital, K has to be written in small. Most of the people do the reverse way. They type K bigger and J small. All in SI system, all the names of the inventors, Joule is a person. His personal name has to be always in capital letter. Pressure, Newton per square meter. N has to be capital, meter square has to be small. So whenever you are using SI system, please be careful how you use the units. Ammonia boiling point, as we saw, 1000 watt per meter square. Delta T is 10 degree. Delta T to 5 degrees. So LMTD is 7.2 degrees centigrade. Using the same equation, Q UA into LMTD, the area required is 48.8 square meter. Let us select 50 square meter standard chiller. So 24-inch dia, 12 feet long, has 683 square feet area, 174 number of tubes, same diameter as condenser, 1.25-inch diameter with 4-pass selection. The brine chiller selection formula, if we use in BTU unit, now since we are following BTU, I said let us follow in BTU also. As I told earlier, 500 is a formula, 8.33 into 60, that is 500 into GPM into specific heat into SG, that is specific gravity, specific heat, into delta T. Q is the heat load in BTU per hour. GPM is flow rate gallons per minute. The brine ethylene glycol, 32 degree Fahrenheit inlet temperature, 23 degree Fahrenheit outlet temperature, mean temperature 27.5 degrees centigrade, evaporating temperature 14 degree Fahrenheit. So brine range is 9 degree Fahrenheit and flow rate is 22 US GPM at 400 feet per minute velocity. Specific heat of brine is 0.9. Specific gravity is 1.03 at 30% concentration. So looking at this chart again, selection, if you go for the on the right hand side extreme, required surface area is given on the right hand side. But brine average temperature we saw 11 or 12 degree Fahrenheit. So first we go to the left hand side, go to the right hand side till you come to living split. Living split is of 10 degree Fahrenheit. So stop at that point and come down to brine outlet temperature. What is the brine outlet temperature? And then go horizontally, and you will get the square feet area required for the brine selection. So these are the chiller selection, ethylene glycol and propylene glycol velocity selections. Normally we select, since the glycols are viscous fluids, we don't stop at 250 fpm velocity like condenser or 300 fpm. We select average velocity of 400 fpm velocity, and that is the at 400 fpm velocity, the velocity factor is 0. So normally the chillers are selected at 400 feet velocity. If you select lower velocity, your multiplier will go up. So your chiller size will become bigger. The chiller selection area required based on this in terms of square feet, same calculations, 24-inch dia, 10 feet long, 452 tubes, 888 square feet. The diameter of the tube is 3/4 inch square feet, 419 fpm velocity. Diameter is selected based on velocity to ensure small liquid diameter. This is for the surge drum velocity. So the surge drum mounted on the top of that is 12-inch diameter, 6 feet long, directly mounted on the chiller, and the pipelines connecting to this are selected on the basis of 75 to 100 fpm velocity. So with 3 connections, pipes of 6-inch diameter are used between chiller and the surge drum. This is the chiller design. The time allotted to me was 1 hour. So I have tried to compress it in 1 hour time. I have given here, if you see my mail ID, ramesh.paranspe@gmail.com. My website is also there, on which all the articles published by me are available free of cost, no password required. You can go and read any of the articles. So there are more than 100 articles which are on the website. My WhatsApp number or cell number is also given. You can send me any question on my Gmail account, either to me or to Mr. Anand Joshi, and we will be very glad to answer all your questions. Thank you very much for listening to me patiently, and good luck to all of you. I hope my presentation has helped you and will improve your design of shell and tube heat exchangers further. Thanks a lot. Goodbye.
Thank you everyone for joining today's seminar. Considering the, Paranspe sir is a very senior fellow, it will be difficult to attend the questions. But we will whatever the questions are there, please send it to Paranspe sir directly or to Association of Ammonia Refrigeration at ammoniaindia@gmail.com, and sir will answer all these questions. And once again, thank you very much for joining. Thank you all.